everybody. So we've been talking about acids and bases, more specifically Bronsted-Lowry acids and bases, and we talked about that a Bronsted-Lowry acid is a proton donor, a Bronsted-Lowry base is a proton acceptor. So the Bronsted-Lowry definition or theory uses conjugate acid-base pairs to explain the transfer of protons. One is giving away the protons, and then one is receiving those protons. So let's look at this example right here. So we have HCO3 minus reacting with H2O to form H3O plus and CO3 minus. So in this case, the bicarbonate ion is behaving as an acid. And the reason I know that is because it gave away a proton. So the HCO3 minus gave away an H plus, so what's left is a CO3 minus. So HCO3 minus, that's your acid. When it gives away its proton, we call this the conjugate base. And then here, water is behaving as the base. And what that means is it accepts a proton. So when the water accepts a proton, it becomes H3O plus. So when the base accepts its proton, we call that the conjugate acid. So the acid has a conjugate base. The base has a conjugate acid. The acid and the conjugate base, or the base and the conjugate acid, look exactly the same, except the acid has an extra H plus. So let's look at this again. The acid and the conjugate base, they look exactly the same, except the acid has an extra H plus. Let's look at the base and the conjugate acid. The base and the conjugate acid look exactly the same, except for the acid has an extra H plus. So the acid portion will always have an extra H plus. So you have an acid with its conjugate base and a base with its conjugate acid. Let's look at this one here. So HCN in this case is behaving as the acid. And so it gives away a proton, gives away an H plus to become Cn minus. So this is the conjugate base. So an acid and its conjugate base look the same, except the acid has an extra H plus. The ammonia here is behaving like the base. And a base accepts a proton. So when it accepts a proton, it becomes NH4 plus. So we call this the conjugate acid. The base and its conjugate acid look the same, except the acid has an extra H plus. Now also, if you look at the reverse reaction, you will see that you have transfer of protons as well. So let's look at the reverse. So this reaction right here, H3O plus CO3 minus reacting to form H2O and HCO3 minus. So this is the conjugate acid, so now it's behaving as an acid. This is the conjugate base, so it's behaving as a base. So an acid gives away a proton. Well, if it gave away a proton, it becomes H2O. A base accepts a proton. If this accepted a proton, it becomes HCO3 minus. Well, let's look at this here, right here. So this is my acid and this is my base. An acid donates a proton. So if this donated a proton, it becomes NH3. A base accepts a proton, so if this accepted a proton, it becomes HCN. So you'll see that when you assign acid with its conjugate base and a base with its conjugate acid, the acid portion, whether it's the real acid, like in the reactants, or the conjugate acid, it will always react donating or giving away a proton. The base or the conjugate base will accept in a proton. So if you wanted to know what the conjugate of something is, if you are trying to get the acid, you add an extra H plus. If you're trying to get the base, you remove an H plus. So if you want the conjugate base of H2S, if you want the base, you remove a proton. So this is the acid. I want its conjugate base, so it's going to give away a proton, and it's become HS minus. If I want the conjugate acid, the acid has an extra H plus, so it should have an extra H plus from this. So this is the base. I want its conjugate acid, so I add an extra H plus. When it comes to acid-base strength, if you have a strong acid, the stronger the acid is, the weaker its conjugate base will be. And if you have a weak acid, the stronger the conjugate base will be. So they're kind of opposite. The stronger one is, the weaker its conjugate. So the stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. The equilibrium will always lie towards the weaker species, never towards the stronger species. So if you have a strong acid, for example, like HCl, it's going to yield a weak conjugate base. Cl minus is a weaker conjugate base. So this side is stronger, this side is weak. If you have a weak acid, then it's not a strong base, but it's a stronger base. So this is the weaker side, this is the stronger side. So let's look at this here. These are the acids, and these are their conjugate bases, or you can think of as these are the bases, and these are their conjugate acids. So you can see that the stronger the acid is, the weaker its conjugate base, and the stronger the acid is, the weaker its conjugate acid. And again, the equilibrium will always lie towards the weaker species. So let's look at this here and try to tell which way the equilibrium will lie. And again, it will lie towards the weaker species. So what we want to do is find these species, here. So HSO4 minus and NH3 here, this is my acid, this is my base, this is my conjugate acid, and this is my conjugate base. I know that because HSO4 minus is my acid. When it gives away an H plus, it becomes SO4 2 minus, so that's my conjugate base. My ammonia is my base, so it gains an H plus to become NH4 plus, so that becomes my conjugate acid. So I'm going to look at my acid here. I'm going to try to find HSO4 minus in here. And so here's HSO4 minus. And I'm also going to find the other acid, which is the NH4 plus. And it's right here. So what you do is you want to compare the two acid strengths together, the acid and the conjugate acid. Which one is stronger? This one's the stronger acid. This is the weaker acid. You're going to do the same thing with the bases. So for the bases, we're looking for ammonia and SO4 2 minus. So ammonia is right here, and SO4 2 minus is right here. Which is the stronger base? Ammonia is the stronger base. And this is the weaker base. So you compare your two acids or your two bases and see which side is weaker, which side is stronger. The equilibrium will always lie towards the weaker side, so this lies to the right. What does that mean? That means when you have this reaction, your KEQ for this reaction will be higher than 1, right? That means that when you reach equilibrium, you will have more of these in solution than you would these. Your products would be more than your reactants. So you're going to have more of the weaker species, not of the stronger species. If you're not given a table like this, sometimes you're given a table of Ka values and Kb values. Ka is the acid dissociation constant, Kb is the base dissociation constant. So you can check those values. Whichever has a higher Ka or a higher Kb is the stronger species. Okay, let's do this equation right here. So H3CO3 minus plus HS minus yields H2S and CO3 2 minus. So this is my base, this is my acid, this is my conjugate acid. Oops, I messed up, I'm sorry. Let me erase that. Okay, start over here. So the HCO3 minus is my acid. I know that because it gives away an H plus to become CO3 2 minus. So that's my conjugate base. This one is my base because it gains an H plus to become H2S. So this is my conjugate acid. So I'm going to look for my acids HCO3 minus and H2S on my table here. So H2S is right here. HCO3 minus is right here. So which one's the stronger acid? Well, H2S seems to be the stronger acid. Okay, let's look at the bases. HS minus is right here, and CO3 2 minus is right here. So which one is stronger? The CO3 2 minus is stronger. This is the weaker species. So which way would the equilibrium lie? It lies to the left, meaning that there are more reactants than products at equilibrium in this case. The weaker species are going to exist more. And that's because that means they don't react as much, right? So they're more stable. The stronger acids or bases are going to react, and so they're not as stable, so you're not going to find so much of them because they would have reacted. Okay, now we know water is covalently bonded, it's molecular, but water slightly ionizes. And so water if you think of this as like an acid, this is a base, well, the acid is going to give away a proton to become OH minus. So this is your conjugate base. The base is going to accept a proton to become the conjugate acid. So you can think of it this way, or you can just simply write it as H2O. So see, it's into H plus and OH minus. Now, again, water's molecular. However, this actually happens, but to a very, very, very small extent. So really the equilibrium lies to the left. It stays mostly as molecular water. Very, very little of it turns into ions. The equilibrium expression, if I were to write, K for this, it would be the concentration of the H3O plus times the concentration of the OH minus. Or if I write it for this, is the concentration of H plus times the concentration of OH minus. Remember we said whether I use H plus or H3O plus, those are synonymous, H plus or H3O plus, same thing. So both of them are saying H plus times OH minus, right? Well, because this is a special process, this is the ionization of water, not just anything, we give it a special name. Instead of just calling it KEQ, we call it KW, W for water. And at 25 Celsius, which is room temperature, standard temperature, it turns out that Kw is equal to 1.0 times 10 to the negative 14. That's a very, very, very small number. Again, that tells you that it all remains as liquid water. Very, very little of it ionizes. If you put a conductivity tester in water, it will not detect any electric current. It will not conduct because there's very, very few ions in there. This is an extremely small number. Now, in water, or really in any neutral solution, for every H plus you also have an OH minus. So the concentration of H plus and the concentration of the OH minus is the same, right? And so if we say that it is equal to X, and this is also X, when we know that this is 1.0 times 10 to the negative 14, we can solve for X. And so it's going to be the square root, which would be 1.0 times 10 to the negative 7th molar. So the water will ionize very, very little. The concentration of the H plus or the OH minus in water is going to be 0.0000001. Very, 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 very small. And in a neutral solution, whether it's water or something else that is neutral, your H plus and OH minus concentration will equal to 1.0 times 10 to the negative 7. So what if I take an acid and put it in water? Well, in neutral water, both of these concentrations are 1.0 times 10 to the negative 7th. If I add an acid, well, what's going to happen? Well, the acid's going to give off more H pluses. So the H plus concentration is going to be higher than 1.0 times 10 to the negative 7th molar. The OH minus concentration is going to be less than 1.0 times 10 to the negative 7th molar. So if I'm given the concentration of either the H plus or the OH minus, I should be able to tell whether that substance is acidic, because if it's acidic, my H plus concentration will be higher than this number, or my OH minus concentration will be lower than that number. If it is equal to that number, then I know that it's neutral. Well, what if it's a basic solution? Well, if I take water, where you have both the H plus and the OH minus concentration equal, and I add some base, well, the base is going to accept some protons. So it's going to take away some of the H pluses that are in water. And so my H plus concentration is going to be less than 1.0 times 10 to the negative 7th molar. And my OH minus concentration is going to be higher. Oops. That is higher than 1.0 times 10 to the negative 7th molar. So I can tell you, hey, I have a solution where my concentration of H plus is equal to 0.004 molar. Is this acidic, basic, or neutral? You tell me, oh, this is acidic because that concentration is way higher than what it would be in water. And if you have more H pluses, that means it's acidic. I could tell you, hey, what if I have an OH minus concentration that is 6.5 times 10 to the negative 3rd molar? You tell me, oh, that's definitely basic because this concentration is way higher than 1.0 times 10 to the negative 7th molar. So if I have too many OH minuses compared to water, then that is basic. I could tell you, hey, what if the H plus concentration is 1.6 times 10 to the negative 10th molar? You tell me, oh, this solution is basic because the concentration of H plus is way less than what it would be in neutral water. So based on the concentration of the H plus or the concentration of the OH minus, you should be able to tell whether it's acidic, basic, or neutral. So in a neutral solution, they're equal to each other and they're both 1.0 times 10 to the negative 7th. In an acidic solution, you have way more H pluses than you do hydroxides, less hydroxides, more H pluses. In a basic solution, you have more hydroxides and less H pluses. So they came up with a scale to measure the concentration or to express the concentration of the H plus. When you get to really small numbers or really high numbers, it's really hard to, think through. If I tell you 1.6 times 10 to the negative 10th versus 1.6 times 10 to the negative 8th, in our brain, those numbers are both really, really small and they kind of mean the same thing, right? When in reality, they're 100 times different. And so they came up with the pH scale, which measures the H plus concentration or H3O plus concentration, whichever you prefer. And pH is equal to negative log of the H plus concentration. So in that scale, I'm going to go ahead and use a different color here. 7 is neutral. That's because in a neutral solution, the H plus concentration is 1.0 times 10 to the negative 7th. If I take negative log of this number, that's going to be equal to 7. If I have a high H plus concentration, like let's say 0.1 molar, well, this is the same thing as 10 to, or 1 times 10 to the negative 1, right? And so negative log of that number would be 1. That's pretty acidic, right? That's a pretty high concentration of H plus. So if you have low numbers, this is acidic. If you have high numbers, this is basic. And so the lower the number, the more acidic it is. The higher the number, the more basic it is, with 7 being in the middle. Notice that 7 is only neutral at 25 Celsius. If you're at a different temperature, then your K is going to be different, and the square root of that number will be different. And so 7 is only neutral at room temperature. But low pH numbers are acidic, high pH numbers are basic. And we've always learned that 0 to 14, in reality, could be lower than 0. It could be a negative number. If it's 10 molar HCl, well, that's a pH of negative 1. or it could be a higher number than 14. So this is like, you know, in general, but you could have higher or lower numbers than that scale. Now, similarly, you can calculate the pOH instead. So the pOH is a negative log of the hydroxide ion. And so it works the same way. So 7 is neutral. That's because in a neutral solution, the hydroxide ion concentration is 1.0 times 10 to the negative 7th molar. And so negative log of that is 7. If I have something that is extremely basic, like let's say the hydroxide ion is 1 molar, well, that would be 0. And so the pOH scale is the opposite of the pH scale, where the smaller number it is, the more basic it is, the higher number it is, the more acidic it is. If you were to add the pH and the pOH of a substance together, it's going to equal to 14, always. Same thing as if you take the H plus concentration times the OH minus concentration of any solution, it's going to be 1.0 times 10 to the negative 14. So let's write that down. So H plus concentration times OH minus concentration for any solution is equal to 1.00 times 10 to the negative 14. If you take negative log of H plus, that's pH, negative log of OH minus, that's pOH, negative log of this number is 14. When you multiply powers, you add them, right? Or logs, I'm sorry, you add them. So pH plus pOH equals to 14 comes from this equation. So these equations apply to any solution. We also know that pH is equal to negative log of H plus, pOH is equal to negative log of OH minus. If I'm given the pH and I want to find the H plus concentrations, the inverse of this equation is 10 to the power. So if I want the H plus concentration and I have the pH, it would be 10 to the negative pH. Same thing with if I'm given the pOH and I'm trying to find the OH minus concentration. So these 6 equations relate to each other and we can use them to do different calculations. Before we do that, let's fill out this table here to kind of look at different substances. So if I have a solution that has an H plus concentration of 1 molar, well, the pH of that is going to be 0, right? Negative log, so this is the same thing as 1 times 10 to the 0. 0.1, this is the same thing as 1 times 10 to the negative 1. So the pH here is 1. Here, this is 1 times 10 to the negative 2, so the pH is 2. This is the same thing as 1 times 10 to the negative 3, so the pH here is 3. This would be 7, so it would be 9, so it would be 13. You need to be able to do these in your head. Just looking at these, write your number as 1 times 10 to some power. Negative of that power is your pH. Okay, this is most acidic here. This is neutral. And this is the most basic. Notice that a difference in 1 pH unit is equivalent to 10 times the concentration. So it is a log-based unit. So if there's a difference of 2, then the difference in the concentration is 100 times. If a difference of 3, then the concentration differs 1,000 times. So for every 1 pH unit difference, it's 10 times the concentration. So it's a significant difference. Okay, now let's look at the OH minus concentration for the same substance. So I know that if I multiply H plus times OH minus, I get 1.0 times 10 to the negative 14. So if I plug 1 molar here and solve for the OH minus, I'd get that this is 1 times 10 to the negative 14 molar. How about this one? If I plug 0.1 here, then this is 1 times 10 to the negative 13 molar. The next one, 1 times 10 to the negative 12 molar. Again, you need to be able to do this in your head. 1 times 10 to the negative 11th molar. This one, if I plug that in here, I'd get OH minus concentration of 1 times 10 to the negative 7th molar. This one, 1 times 10 to the negative 5th molar. And this is 1 times 10 to the negative 1st molar, or 0.1 molar, right? If I want the POH, I take negative log of the OH minus concentration. So this would be 14, this would be 13, 12, 11, 7, 5, and 1. Notice that if I were to add my pH plus my POH, I get 14 in every case. Also notice, same thing that we noticed with the pH, a change in a pH unit of 1 is equivalent to a change of 10 times the concentration of the OH minus. Also note that the higher the pH, the lower the POH. The lower the pH, the higher the POH. So they're kind of inverse. Neutral is 7. Acidic substances, you have low pH, high POH. Basic substances, you have high pH and low POH. With concentrations, something that's acidic has a high H plus concentration and a low OH minus concentration. Something that is basic has a low H plus concentration and a very high OH minus concentration. So it can get confusing. So I would, if you're asked, is it acidic, basic, or neutral? There's so many different ways to look at it. You can look at the H plus concentration, you can look at the pH, the POH, or the OH minus. So I would stick to one thing. I think you guys are most familiar with pH. So whatever you have, always convert to pH, and then you can tell if it's acidic, basic, or neutral.